All right, so I'm starting the recorder, just in case anyone wants to check. It is already started, and the audio is doing good. We are recording the sound as well. All right. So what we'll do today, the focus of today's lecture is going to be comparison of numbers. I think we started on that one last Thursday. So we're going to continue today and kind of finish it. The lab activity today is related to that as well, to comparison. All right, so comparison is closely related to subtraction. In other words, we're performing the same operation as regular quote-unquote subtraction, but we don't care about the actual difference, okay, the entire number of the difference. We talk about most of it, okay? But we focus on a few what we call flags, okay? One flag, a flag is basically just a Boolean value. It's a 0 or 1. It's just that, we use the word, flag instead of a bit, okay? Because it is indicating, which way we should go. Okay, so this is the basis of how we can perform branching in assembly language programming. In C and C++, it's pretty easy. You just say if, blah, 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 and then you specify the then branch, else, and then you specify the else branch. Or if you have a loop, you specify while, and then the condition, the stay in loop condition, and then you specify the body of the loop. And it automatically does all the right thing, okay, to stay in the loop or to get out of the loop. But when we are dealing with assembly language, it is not quite that easy, okay? So let's go ahead and take a look at comparison. Okay, so I got the right slide already. And this time we'll kind of take it a little bit slower than last time, simply because this class is already quite a bit ahead of the other class, because the other class missed one Monday already, and then there'll be another Monday that they will be missing. So I don't want this class to be like 2 classes ahead of the other one. All right. So we already talked about how knowing whether a value is less than another value is enough. Okay. In other words, just having the less than operation and then have all the Boolean operators like negation, conjunction, and disjunction, that is enough for us to imitate or to emulate all of the other ones. So if you just give me less than and all the logical operators, I can use less than to deal with greater than. That's an easy one, right? Because you just flip the order of the comparison, then a greater than becomes a less than. Okay, that's an easy one. If you want less than or equal to, then I can use less than, but I also put an exclamation point or the negation on the outside. In other words, if you want me to tell you whether x is less than or equal to y, I can tell you whether it is not the case that y is less than x. They mean exactly the same thing. So, we kind of went through this portion already, I believe. And the more difficult ones is not equal to, which boils down to x is less than y or y is less than x. And this is also why in some languages, not equal to is specified by less than, greater than, because it's less than or greater than. Okay? And then once we have not equal to, defining equal to is just the negation of that. So that's why we just need less than. And then the module continues to talk about unsigned comparison. So we'll kind of go through this a little bit, even though this is a proof where this is not a class, this is not cisp310, so proof is not the focus of this class. But it is still kind of useful to understand how it works or why it works. All right, so are there any questions about these two statements? That 0 as a value is less than 1 and 1 is less than 0 is false. We all agree to this? Okay, cool. So once we have this, then we have the usual notation. In other words, we use x subscript I to represent the ith bit of x, starting from 0. So the least significant bit is bit 0. And then we do the same thing for y. So y subscript I is bit I of y. All right. And now that we have all the digits of xi, each one is a single bit. We want to know the following. Okay, we want to confirm that 2 to the power of n is greater than the summation of sigma I equals to 0 to n minus 1 to the power of I. So if you plug in certain values for n, you will know for sure that, okay, it works, right? So let's plug in n equals 3. When n equals 3, then on one side we have 2 to the power of 3, which is 8. On the other side, we are adding 2 to the power of 0, which is 1, plus 2 to the power of 1, which is 2, plus 2 to the power of 2, which is 4. 1 plus 2 plus 4 is 7. 8 is greater than 7. So this particular statement is true when n equals to 3. Is that making any sense? So it's a concrete example of how this statement is true. But can you say this statement is true for all non-negative n's? You have a probably good idea that it's probably true, right? But can you just say that, yeah, it looks like it's true, and then we'll just take it for granted? Maybe in this class, but in general, you don't want to take it for granted. So if you don't want to take it for granted, you have to prove it. So how do you prove something like that? In other words, this is the statement that I want to prove for all values of n that are positive. So when n equals to 1, I want this to be true. When n equals 2, I want it to be true. In fact, I want n to be any arbitrary positive integer, and I still want this entire statement to be true. How do I show that this statement is always true? So that's my question. What do you think? Proof by induction, very good. So proof by induction, okay, this is not a proof class, so if you don't quite get what is proof by induction, it's okay, it's not a problem. But if you have taken CISP 440 already, then you might understand, oh, okay, so this is another application of proof by induction. So proof by induction requires a base case. So the base case is basically saying, can we lock down the value of n and just say that the expression that we want to prove is true for that particular value of n? So we just want to lock down n to the smallest value that we care about. So in this case, the smallest value that we do care about is when n equals to 1. So then you look at this expression here, you look at the statement that I want to prove to be true all the time, and you say, okay, when n is 1, what is 2 to the power of 1? 2, okay? What about the other side? Okay, even though it looks really nasty, it becomes really simple. Because when n is 1, 1 minus 1 is 0. So the index I only has to go from 0 to 0, which means we only got one term, which is 2 to the power of 0. What is 2 to the power of 0? 1. 2 is greater than 1 is true. I have proven the base case already. So the power of proof by induction is you can use the induction step. The induction step is really, really interesting. The induction step starts with an assumption. So the assumption is, okay, let's just take n equals to k. Okay, so when n equals k, then 2 to the power of k is greater than the summation of I going from 0 to k minus 1, 2 to the power of I. Okay, and we don't even say which k are we using. I'm just making the assumption. Let's say that whatever is highlighted on the board here does work for n equals k. That's an assumption. But we make that assumption as part of the induction step when we prove by induction. Okay, so if we make that assumption, then what we really want to do is to prove that the statement is also true when n equals to k plus 1. That is the induction step. So how do we prove that? So we look at the statement that we actually want to prove, okay, which is this one. How did I go from the first line to the second line? Let me scroll up a little bit. How did I go from the first line to the second line in the proof? What happened to the left-hand side? Yeah, exactly. 2 to the power of k plus 1. This plus 1 can be separated to 2 times 2 to the power of k, which turns out to be just 2 to the power of k plus 2 to the power of k. Is that okay? I didn't do anything to the right-hand side, but I could do, and then what about from here to here? What just happened?
You subtract 2 to the power of k.
Exactly. I subtracted 2 to the power of k from both sides. Because on the left-hand side, it's pretty clear. If I take away 1 to the power of k, we only got 1 left. But the right-hand side has 1 to the power of k in the series because that's the last item. So when I take that item out, then I just go like, oh, we have 1 fewer term. The last term is now when I equals to k minus 1. So I get this expression left. And then I go like, I'm done with the proof. Because that is exactly what we assumed to be true to begin with in the induction step. Question?
I know this isn't a proof for any class, but can you just kind of explain how, like I've seen proof by induction before and done it, but can you explain how getting to our assumption proves our assumption?
Okay, so the assumption of the induction step is really the trick. Okay, so the way I explain, so your question is not pertaining to this particular proof. You're basically asking about the technique itself. Yeah. Yes. It's okay. Okay, so it's actually pretty easy. So imagine that I'm stranded on an island here. Okay, that's the cruise ship. Okay, and there are turtles along the way floating. Okay, so the idea is, can I walk on the back of all the turtles to get to the cruise ship? Is that okay? All right. So induction step is first proving that I'm not sinking. I'm standing on something right now. Well, I'm on the beach. Okay, so I'm definitely standing on something solid. I'm not sinking. Is that okay? So the induction step is saying, let's say that you are on, not solid ground, but you're on something that is either floating or solid ground. Can you prove that there's one thing ahead of you, just one step further, all the time? So if you can prove so it makes the assumption that you're stepping on something, you're not sinking, and it's asking, if you can assume that you're not sinking right now, you're stepping on something, can you always prove that there's something ahead of you that you can also step on? If you can prove that, that means, hey, I'm standing on the beach right now, but because of the induction step, I know I can step on the first turtle, right? But while you're on the first turtle, the induction step is also saying, hey, rest assured, there's turtle number 2. When you step on turtle number 2, the induction steps, there's always a turtle number 3 within a step. Is that making any sense? Sort of?
I know, it's a tough question.
Yep.
That doesn't mean what? Why is it not that the 2 to the k plus 1 formula is not the assumption? Because it looks like you took that and showed that the sum from 0 to k minus 1 is what follows.
So the assumption is this one. So the idea is the assumption is not locking down the value of n. It is just saying, okay, because you want this to be true for any value of n. In other words, when you're on the back of any turtle, there's always a next turtle. That is what you're trying to show. Am I answering the question? Or?
No, I get that, but I thought the idea is that you assume one thing, and you show that for any integer after that, that the k plus 1 case follows. So why is it the 2k plus 1 formula is not the assumption?
The assumption is one value smaller than what you want to get to. Yeah, but it can work backwards too. In other words, in some cases you have to work backwards. In other words, if you have a case where you want to prove for all integers, positive and negative, then you might want to choose 0 as your base case. Then you have 2 induction steps: one to go to the positive integers, and then the other one to go to the negative integers. It's just that in this particular example, we have a really easy base case because it's bound on one end anyway, so we just use that as our base case. Yep.
So if it were not true, then
if what is not true?
If the assumption was not true, then you wouldn't be able to get back to the original because it would be unproportional.
So the assumption is never proven. Okay, the assumption, as the word implies, is really just an assumption. So you're basically saying, let's assume that I'm already on the back of a turtle. Can I always be sure that there's a turtle within a step's distance? If you can prove that, then you can start walking to the cruise ship, knowing that you will get to the cruise ship. Is that okay?
Yeah.
Yep.
So in the steps of the proof, you go from what you're trying to show to the assumption. Is that always the direction that you go in? Does it matter?
Okay, so there are two distinct steps. Let me highlight the two distinct steps. So the first step is you always want to establish a base case. So this portion is called the base case, which means you lock down the value of n, which is the variable, to the smallest possible value that works in your proof.
I meant the steps.
For the induction step?
How the proof goes, like those steps.
Yep.
Specifically.
Yep.
So it doesn't matter if you're running from the assumption to what you're trying to prove or what you're trying to prove to the assumption.
You want to state the assumption first.
Yeah.
Yeah, you want to state the assumption, and then the only difference between the assumption and where you want to go to is off by 1.
Yeah.
Yep.
Okay.
Yep. So that's the usual direction.
Okay.
Yep. But the induction step can also go in the negative direction. So in some cases, not in this one, you would basically say 2 to the power, okay, n equals k is the base case, not the base case, but the assumption in the induction step. But then you want to go to n equals to k minus 1 as the next step. Yep.
So is it a proof that the assumption is happening rather than the truth of the assumption?
Okay, so the idea is, the assumption itself, we know at least one case is true, is when k equals to 1, right? So we do have a solid ground to connect to. So now the question is, if I get onto the back of the first turtle, can I move on to the second turtle? If I'm on the back of the second turtle, can I move on to the third turtle? So that's what you're saying, if I'm on the back of turtle k, do I know there's a turtle k plus 1 that I can step on?
Rather than like the truth of the turtle holding you up.
Right.
I think I get it. If you start at 1,
Yep.
and then you prove that there's always a next one,
Yep.
it doesn't matter where you start.
Right, but that means that both steps are important. Just being able to prove the induction step is not sufficient, because that simply means that if you are on the back of a turtle, there's always a next turtle. But can you start on the back of the first turtle? Without the base case, you cannot state that. Is that okay? And I can almost be sure that most people walk out of this class just remembering the turtles and the cruise ship, and not proof by induction. Yeah, remember there's a proof technique that involves turtles and a cruise ship and an island, and tech. Okay, so that is kind of significant, because once we have this proof, then we can basically say, oh, give me any n that is a positive integer, this has to be true. Is that okay? All right, so it is significant. Why is it significant? We'll take a look later on. So now we look at x and y, and we want to kind of lock down to a certain number of bits that we use to represent integers. Because in theory, integers can be as large or as small as you want them to be. So you cannot really say, oh, integers only have X number of bits. But when you are programming, your integers have fixed width. Okay, 32 in the past, 64 these days, possibly 128 in the near future, and so on. So we want to lock down and say we're dealing with m-bit integers in our processor. But you don't really have to go too far to make this assumption, because you can always claim that for any integer I that is greater than or equal to m, those bits are all zeros. In other words, you just kind of assume that you have a whole bunch, infinitely many leading zeros of the values that you're dealing with. Okay, right? If they're not stated, you can always say they're zeros. So then what we want to do is I don't think this notation was ever needed, but I'm just using this to represent a subportion of the integer. So this is basically a p plus 1 bit integer. starting with bit 0 all the way up to bit p, so it's a portion of the integer, but I don't think we actually need this notation. So let's go ahead and look at my claim here. So the claim is, assume that xi equals to yi for some p for all the I greater than a certain p. In other words, we cannot determine whether x is less than y or not, because, up down to bit p plus 1, because they're all the same. Yep.
The pth bit is still within n bits, right?
Possibly, but it doesn't even have to be within m, because remember, both numbers have leading zeros. So we are basically just saying, okay, ignore all the bits, all the most significant bits that are identical, because they are not telling us the ordering of these two numbers. Is that making any sense? Okay, all right. So now we say, okay, what if they're different? So what if we start from the most significant bit, and then we're moving down and down and down until we find a p such that bit p of x is a 0, bit p of y is a 1, okay? Then can we conclude x is less than y? Regardless of what is the less significant bits. And why can we make that conclusion? Because of the thing that we proved earlier, okay? Which means if bit p of y is a 1 and bit p of x is a 0, even if all the bits of x to the right hand side, the less significant side, even if they're all 1s, this 1 here in bit p of y is going to make y greater than x, period. And that's why we have that little theorem to prove earlier, because we are relying on that theorem to come to this conclusion. Is that okay? So if you're scanning from the most significant bit until you find the first bit that is different, if x has a 0 and y has a 1 for that particular bit position, you can conclude right away and say, okay, x is less than y. Done. You don't have to look any further. Okay? The reverse is also useful, because if bit p of x is a 1 and bit p of y is a 0, then we don't have to look any further. Y is less than x has to be false. So you basically use this approach and keep going until you can make this decision and go like, okay, we have a conclusion. Or you keep scanning until p is 0. When p is 0 and you cannot tell the order, then the two numbers are the same, which also means x is less than y is also false in that case. Is that okay? So is this logic working okay with you guys? Okay?
Actually, I have a question about that. So the point of having p is just to kind of separate it from the whole m thing, because p could be any size?
Yeah. Yeah, so p can be smaller than m, or m itself, m minus 1. Okay? But this is great, okay? But it doesn't help us, because just knowing this part here, we can look at the numbers and manually using eyeball algorithm and say, oh, the first number is smaller, or the second number is smaller, or they're the same. Okay, but how do we use a subtractor and use most of the circuitry that we have already talked about to decide whether x is less than y? That is the question. Okay, so the question is, do we already have enough logic, enough circuitry to make that decision? And the answer is yes. Okay, but to get to that answer, we are gonna jump through some more hoops. So we are going to use v of x to represent the value represented by x. X is a number, is a binary number. So v of x is just the value represented by that bit pattern. V of y, once again, is just the value represented by the binary number y. So this is a claim, okay? I make this bold claim and say that the value of x, the binary number x, is less than the value represented by the binary number y, if and only if Tm, okay, that's the borrowed bit at bit position m, is a 1. And remember, we're dealing with m-bit integers. Is that okay? So this is my claim. Without any proof, I'm just saying that if you look at the borrow out of a subtractor, that by itself is going to tell you whether x, the minuend, is less than y, the subtrahend, or not. Okay? But can we prove that? Because if this is true, that means we already have everything that we need to tell whether the minuend is less than the subtrahend, because we already talked about the borrow bits for a subtractor and how to compute it quickly using the borrow look ahead mechanism, right? So we are trying to link all of those dots together and say, can we be really lazy and not to make any new circuitry to perform comparison? Okay. So what we'll do is we're going to revisit how we define the borrow bit. So the borrow bit at position I plus 1 is basically the borrow of xi minus yi. Remember, x is the minuend and y is the subtrahend. Or the borrow of qi minus ti. Qi is the intermediate difference, and then ti is the borrow of bit I. So I'm hoping these notations are getting familiar, because this is pretty consistent with the previous module that talks about binary subtraction. So are we doing okay so far with this definition? It's basically just a revisit of something that we already talked about. So we're going to put this into our quote-unquote proof, and we're going to say we will make the assumption that xi equals to yi for all the i's that are greater than p. In other words, we are quote-unquote ignoring, okay, all the most significant bits that are identical. Oh, is that okay? But on top of that, I'm also saying that ti equals to tp for all of these. In other words, if you have the most significant bits being the same, the borrow bit for all of those is going to be the same as the first bit position that is different. Is that okay? So in your mind, just draw a picture of identical bits, as most significant bits, on the left-hand side, a bunch of those are the same. So what this is claiming is the borrow bits for all of those bit positions will be identical. In fact, they will all be the same as TP. So when you get to bit position P, this is the most significant bit that shows a difference. Okay, the X and the Y are different at this bit position. Is that okay? So we're getting back to the exercise a little bit earlier, but this time I'm not using, I'm not just arguing, using comparison. This time I'm using the definition of the borrow bits. Okay, so if xp is in fact a 0 and bit yp is in fact a 1, can we accept this equation here? The borrow bit of position p plus 1, the next one, is the borrow bit of 0 minus 1, because it's x minus y, or the borrow bit of 1 minus something else. So now the question is, we know this 0 comes from the x, we know this 1 comes from the y. Who's responsible for this 1? It's our q. It's qi, right? But why do I know for sure that qi is a constant of 1 in this case? Because I know what x is, I know what y is. X is a 0, y is a 1. How do we define q, the q term? Exclusive or, exactly. Or whether x and y are different, right? So knowing that x is a 0, y is a 1, I know the q term has got to be a 1. Now why is that useful? Because the borrow of 1 minus something is always 0. This term is always a 0. But this term is always a 1. In other words, now we know t plus 1 is going to be a 1. And then what we can do at this point is we can now backfill all the more significant borrow bits to be 1s as well. Is that making any sense? But how can we backfill all of the more significant bits? What is the mathematical basis for doing that? Yes, go ahead.
Well, so assuming that they're all the same, you can just, we'll say for arbitrary sake that they're all zeros. If the borrow bit is 1, you're always going to have 0 minus 1, and then there'll be a 1, 0 minus 1.
Right.
And then so if they're all 1s, and the borrow is 1, you have 1 minus 1. Oh, you still always have that.
Right, but what do we know about the more significant bits? All the bits, to the left-hand side of position P. What is the assumption? X and Y have exactly the same digits, right? So that means this and this are the same. They're either 1, 1 or 0, 0. What is the moral of subtracting 1 from 1? 0. So what is the Q? 0. That 0 goes here. 0 minus 0 always has a borrow of 0. Cool. But it also gives you a Q of 0. Okay? This, on the other hand, will now become the borrow of the less significant bit, which starts with P, position P. But if we know that position P has a borrow of 1, that 1 goes in here, when this is a 0. 0 minus 1 is a borrow, so now you can back propagate or back fill all of the more significant borrow bits until you get to bit position M, which is what we want. Is that okay? Yep.
Can you just explain really fast how you knew the question mark was a 0?
The question mark is not a 0. The question mark is going to be 1, but this is going to be a 0.
No, not in the backcode.
Oh.
In this.
In this one, it doesn't matter. The question mark can be a 0 or a 1, but it doesn't really matter because this B is already giving us a borrow of 1, so it doesn't really matter what the other one is going to be. Okay? Yep.
Position P isn't necessarily the bit position of the most significant digit of whatever integers that we're working with. It's the first that X and Y are different.
Yes, that is correct.
Regardless of if there are numbers before.
That is correct.
Okay.
So position P is the most significant bit that shows a difference.
Got it.
Okay? So are we good so far? Okay. What if position P, because we know X and Y are different at position P, but this time, X has a value of 1, Y has a value of 0. Can we come to a conclusion and use the borrow bit to indicate, hey, we got a conclusion now. X is not less than Y. Can we say that for sure? That's the question. All right, so when X is 1, Y is 0, the result is going to be a 1. So we know that QP is going to be a 1. That is simply because of the definition of how we define the Q term. TP plus 1, okay, let's work this out. We know that this 1 is the X, this 0 is coming from the Y, and when you subtract a 0 from a 1, the borrow is always a 0. Okay. But we want to make sure that this TP plus 1 is also a 0, but we got a second chance. We have to make sure that the other side is also going to be a 0. So now we have this borrow here. This is a 1, and now we have this question mark here. So how do we know that is also going to be a 0? Just this part here. How do we know that is a 0? You subtract anything from a 1, it won't be borrowing. 1 minus 1 has a borrow of 0. 1 minus 0 also has a borrow of 0. So that means the second borrow function is always going to give us a 0. So from here we can say this is a 0, this is a 0, 0 or 0 is guaranteed to be a 0. And now we can use TP, which is a 0, and use it TP plus 1, which is a 0, and backfill it all the way back to bit M. Is that making any sense? Now, how can we backfill? When we are backfilling, the assumption is the more significant bits are identical, which means these two bits will both be either 1, they will be 1, 1 or 0, 0. In either case, when you subtract a 1 from a 1, you have a borrow of 0. If you subtract a 0 from 0, you have a borrow of 0. So for all of the more significant terms, this is guaranteed to be a 0. But we also know that this is going to be a 0 as well, because it is referring to the one bit that is less significant. But we already know that p plus 1 is a 0. So that's how we can backpropagate or backfill all of the more significant borrow bits, that they're all going to be zeros. So that's how we can use the borrow bit overall, the borrow at bit position m as an indicator whether the minuend is less than the subtrahend or not. Is that okay? Are there any questions? Yep.
So you got the TI by TP plus 1.
Okay, hold on. Which part are we talking about?
How did you solve for TI?
How do I solve for TI? You mean here?
Or you just said it equal to...
We are backfilling all the i's where I is greater than p plus 1. We just determined what is p plus 1.
Yeah.
But once we solve p plus 1, we can backfill p plus 2, p plus 3, all the way to m. And the reason why we can backfill is because those more significant bits, x and y are the same. So that means this term here is going to be a 0. But we also know that the less significant borrow, this one here, is also a 0. So that's how we can guarantee if a 0 here is a 0 here. So p plus 2 is guaranteed to be a 0 because of that. Then p plus 3 is guaranteed to be a 0 also because of that. Okay, let me just write it down because I think it might be helpful to just kind of write it out. Because when we expand the equation, it will be kind of clear how we can do that. So let me turn on the tablet. Okay. Okay, so I'm going to write it down here. Bit P is the most significant bit that is different between x and y. Is that okay? Okay. So it has two ways to go. Okay. So that means we have one scenario where xp is a 0, yp is a 1, and then the other scenario is when xp is a 1 and yp is a 0. Can we accept that? Okay, because this is the only two ways where the two bits can be different. One is a 1, the other one is a 0. Is that okay? All right. Okay, so once we know this, we also know qp is a 1, and the other side is also qp is a 1. Can we take that? Can we accept that? Okay. We don't know anything about TP. TP can be something that is unknown because that depends on the bits that are less significant than position P. So all the bits of x and y that are like bit position P minus 1, P minus 2, and so on will determine what is TP. But I'm saying that that is not even important to me. Yep.
Is it possible to have a bit that is larger than P?
A bit that is larger than
Like that, the position P, because P is the first.
the most significant.
Yeah, P is the most significant, but it's difference between 1 and 0. So even if it's a 1, it's 1, 1, so that's a 0, 0, 0.
The more significant bits are all the same. Okay? So are we okay so far? Okay? So now what we really do care about is P plus 1. That is what we really want to know. So when we look at the equation, okay, in this case it is B 0, 1 plus B, and then we have a 1 here, and then the question mark here. Okay, so this is the same stuff in the notes, right? Because I'm hoping you guys can see how this is resembling stuff already in the module, right? Okay. This 0 is that 0. That 1 goes here. That 1 goes here, and this question mark goes here. Is that making any sense? All right. So even though we have one unknown, doesn't matter, doesn't bother me at all, because this is guaranteed to be a 1, and 1 or whatever is always a 1. So that means we know P plus 1 is a 1. Great, but we don't really care that much about P plus 1. We only really want to know what is T subscript M, which is the borrow of the most significant bit. Okay. Okay, so let's check out P plus 2. Okay, I'm just going to go through a few steps. Okay, what is that going to look like? Plus B of something. Okay. So this is the general format of the borrow flag. Okay, but what do we know about these two positions? Remember, these are more significant digits.
P plus 1 of the second B.
They are the same. Because because that's how we found position P is the most significant bit that is different, which also means the more significant bits, if there's any, are guaranteed to be the same. Okay, so if they are the same, then that means they can be both be zeros or they can both be ones. But either case, this term becomes 0, right? If you subtract 0 from 0, it has a borrow of 0. If you subtract 1 from 1, it also has a borrow of 0. So it doesn't really matter which way it goes. Let's check out the second one. What goes here? What do you think would go into here? Do we know which constant will go here?
0.
It's going to be 0, okay? Because that's the Q term, which is the exclusive OR. That's the exclusive OR between these two values. So that is guaranteed to be a 0. Now, since we are talking about P plus 2 to be exact in this case, do we know what goes here?
1.
How do you know it's a 1? Because we just scroll up a little bit, right? This 1 comes from this 1. Is that making any sense? So subtracting 1 from 0 has a borrow of 1. False or true is true. So now we know that P plus 2 is also a 1. But tag, that is not M. So what do we do? You just repeat the same thing, right? Until we get to M. So is that intuitively making sense? Okay. So the other side is kind of the same thing, except we are propagating 0 all the way to Tm instead of propagating a 1 to Tm. Is that okay? So what is the bottom line? Okay, if you cannot remember all the steps of the proof, and it's not the focus of this class, what are we going to take away from this discussion? The takeaway of this discussion here is this theorem. So once again, what is that saying?
X is less. Yeah.
The value represented by the binary bit pattern X is less than the value of the binary pattern Y, if and only if the final borrow or the borrow out is a 1. But that's only from the unsigned perspective. Okay, we are not using signed interpretation when we talk about the borrow flag. Is that okay? So are we kind of convinced, mathematically speaking, okay, that the borrow flag alone is enough to specify whether the minuend is less than the subtrahend when values are unsigned? Okay, I mean intuitively it makes sense, okay, because why do we call that flag borrow? because you don't have enough. So if you don't have enough, that means the minuend is less than the subtrahend. So intuitively, it makes sense. But when we boil down everything to binary operations, we still want it to make sense. And this is how I, just rigorously prove that the borrow flag itself is sufficient to indicate ordering. Now remember, I'm not going to ask you guys to prove anything in the exam. So this is really kind of, for the most part, it is to convince me more than you that this is the right thing, okay? But I think it is important that at least you look at this and go like, yes, now I'm convinced as well. Is that okay? All right. So if this is okay, then we move on to signed values. So signed interpretation is a little bit tricky, okay? So the value of a bit pattern as an unsigned representation is this. Okay, so let's take a look at this monster here. Okay, just the first row of the monster. So we're focusing on the first row here. That looks really ugly, right? What is that question mark and the colon doing here? Well, there's a reason why C and C++ is the prerequisite of this class, right? So I can make that assumption and go like, yes, I know you know this operator already. Okay, what is the name of that operator? The ternary operator. What does it do? It's an if then else. Okay, very good. So which part is the condition? Which part is the then? Which part is the else?
Condition is on the left of that question mark.
Yep.
The then is on the right of the question mark.
This is the then, and this is the else. Okay, so very good. So just to summarize what a ternary operator is, in case you kind of do not remember it, this is the condition. If the condition is true, then and only then we evaluate the then expression, which is between the question mark and the colon, and then the value of the then portion becomes the value of the entire expression. Is that okay? If the condition is false, then we ignore the then expression entirely. We don't even bother to evaluate. And then we evaluate the else expression, which is whatever is to the right-hand side of the colon. And then whatever the value of the else expression is, becomes the value of the entire ternary expression. Is that okay? Do you think in general, not in this case, but in general, can the then or the else expression itself be a ternary expression?
Yeah.
Yeah, you can nest ternary expressions. And a lot of people do not know that you can actually express a lot of stuff in C and C++ without the use of statements. You can use expressions to do a lot of work without even using statements. But then your program would not be very easy to read.
Ternary stops reading when you have nested.
You just have to use multiple lines and.
Well, yeah, if you white space that like crazy.
Yeah, and indent and use the parentheses on their own lines and stuff like that.
I once made the mistake at work of doing like 4 into each other, and it was a nightmare to try to fill it out. It was switch case in the end.
Okay. All right, so this is actually a pretty ugly way to look at it. Okay, so what is x m minus 1? It's the most significant bit of x. Why is it minus 1? If x has m bits, okay, then why is x subscript m minus 1 the most significant bit? Because we started with 0, exactly. So this is in fact the most significant bit. So this is basically saying if the most significant bit is a 1, if it is true, then we evaluate the rest of the bits, but then we negate it because it is negative. If not, that means the rest of the bits are indicating just the quantity to the positive side. We just kind of add up all of those. Is that okay? Any questions about this part? Okay. How did I go from here? Okay, let's take a look at the then expression first, which handles the case when x m minus 1 is in fact a 1. So why do you think, okay, first of all, what is this portion? This portion looks exactly the same as this portion here. it is looking at all the bits, and it is multiplying each bit position to a power of 2, and it's taking the sum of those things. So it's really just adding all the bits, right? But that is unsigned. What am I subtracting it from? 2 to the power of m minus this. Have we seen something like this before? I think in the previous class we talked about something like this. Remember the 16 minus x thing? It's the same thing, except we're not locking down to only 4 bits, okay? But we have one final negation on the outside, because this part only indicates the magnitude, so we have to do a negation on the outside to look at the actual value. Is that okay? In other words, we can look at this as 2's complement. Okay, how do we go from here to here? What changed in this term here? Yeah, you can say that. And then I flip the order. Okay, so the negation of this, okay, double negation, becomes a positive, and then this guy becomes just a negative. So I just move it on to the other side. Okay, and then what did I do from here to here? Yep, I pulled the last term out of the sigma to be on this side. Okay, and what about this one here? It lost a term, didn't it? Or did it? It lost a term, but why can I lose that term? If I evaluate this part here, that means the condition is false, right? If the condition is false, that means x subscript m minus 1 is a 0. So it's okay for me to lose the last term, because x subscript m minus 1 is a 0. It doesn't contribute to the sum in any way. So that's why I can lose that term. And how did I go from here to here? Oh, I just put that term back in. And then over here, what did I do? Okay. How did I go from here to here? Okay, first of all, what do we know about x subscript m minus 1 when we are evaluating the then expression? It's a 1. Okay. So just kind of ignore this, it is a 1, just ignore this, it is a 1. So what we're really dealing with is 2 to the power of m minus 2 to the power of m minus 1. What is that? 2 to the power of m minus 1. Is that okay? Because x subscript m minus 1 is known to be a 1 if we are evaluating the then expression. So whether we specify x subscript m minus 1 or not, it doesn't make any difference. We know it is a 1 already. Is that okay? So the idea is I want to equalize these two. I want to make the then and the else side identical. Okay? And I have just accomplished that. Because when you look at this, this extra parentheses is not needed. This extra pair of parentheses is not needed either. In other words, whether x subscript m minus 1 is a 1 or a 0, it doesn't matter. We still want to use the same expression. So that's why I can summarize everything to one single expression now. Yep?
Can you explain one more time how you took out the 2 to the m in the second step up?
You mean here?
Yeah, how did you take out the 2 to the m again?
Okay, so we know this part is a 1, right? So we have 2 to the power of m minus 2 to the power of m minus 1, because this part is just 1. Is that okay? But what is the other way to express 2 to the power of m? It is 2 to the power of m minus 1 plus itself. Right? Okay, so this portion, the highlighted portion, is 2 to the power of m minus 1 plus 2 to the power of m minus 1. But I just subtracted 1 over here. So that's why I only have one. I only have 1 to the power of m minus 1 left. Is that okay? But the idea is I'm just playing with this whole thing so that I can come up with one single expression. Whether the sign bit is a 1 or a 0, I have one expression to do it. Is that okay? All right? All right, so why is that important? So this is why okay, so I explained here, because of this term here, this is also why the most significant bit of a binary number, when it's interpreted signed, the most significant bit is also known as the sign bit. Because when x subscript m minus 1 is a 1, it turns the whole number to a negative value. Is that okay? But hold on a second here, Chad. Are we really sure that this entire summation, if all the x here are 1s, is not enough to counterbalance this term here that would make the entire term negative? How do we know that? Very good. It is the proof that we did a little bit earlier. Okay? So once again, you know, the parts of this module, individual parts, they are kind of useful, you know, in multiple parts of this discussion. All right, so that makes signed comparison seemingly very easy. Because, okay, let's see if we can follow this line of reasoning. If x is less than y if and only if x minus y is less than y minus y. Can everybody buy that? I'm taking y away from both sides.
Yeah.
Okay? Does it matter whether y is positive or negative?
No.
No. Okay, very good. So we can buy the first two lines. Okay. What about from here to here? In other words, you know, are you sure that y minus y is 0? Cool. Okay. Wait. If x minus y is less than 0, it means it's negative, and every negative value represented in binary in signed representation has the most significant bit being a 1. Is your light bulb blinking? Let me say that one more time. From an earlier discussion, we know every negative value represented in binary but in a signed representation, all the negative values will have the sign bit being a 1. Okay? But now we are saying if x is less than y, then x minus y is a negative value. Which means the sign bit of the difference is going to be a 1 or a 0. It's going to be a 1. Okay, so that seems like we can use the sign bit of the difference, which is a d subscript m minus 1, the most significant bit of the difference, to indicate whether the minuend x is less than the suffragand y or not. Does it make sense?
Yeah.
We just use the sign to indicate, okay, x is less than y if and only if the difference is negative. But it doesn't work that easily. That would be way too simple, right? Okay, so why do we have a problem here? Let's go ahead and use the tablet, and we'll go through a few problem cases. So the problem cases, okay, so we'll specify we are dealing with 4-bit numbers. In other words, m equals to 4 in our examples. Okay? We'll go through a few cases where everything is cool, no problem. Okay? So we'll say, let's deal with -2, x is -2, and y is -3. Okay? So now we are asking the question, if we subtract y from x in binary subtraction, is the sign of the difference going to be a 1? Excuse me, it's going to be a 0 because -2 is not less than -3. Right? Let's work it out. -2 is 1, 1, 1, 0. -3 is 1, 1, 0, 1. We do the subtraction. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1, 1 minus 1 is a 0, and then we have no borrows here. And then once more, 1 minus 1 is a 0, 0 minus 0 is a 0. The borrow flag is not even important because we're dealing with signed comparison. But the bottom line is, you look at the sign flag here, or the sign bit of the difference, it's a 0, which means the middle end is not less than the subtrahend. -2 is not less than -3. Seems to work. Is that okay? All right, so let's try another one that works. That works okay. We'll try 1, 1, 1, 0, which is representing -2, and this time we compare it to 1. So this time -2 should be less than 1, and the sign flag of the difference should be a 1. Okay, but we'll go through the actual subtraction and make sure. Okay, 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0, no borrow. 1 minus 0 is a 1. 1 minus 0 is a 1, no borrow. 1 minus 0 is a 1. 1 minus 0 is a 1. And the sign of the difference is in fact a 1, which indicates that the minuend, which is 1, 1, 1, 0, representing -2, is less than the subtrahend, which is 0, 0, 0, 1, representing the value of 1. Everything is cool, not a problem. So far, so good. Let's break it, okay? So now we go like, okay. So when is this not going to work? Why can't we just use the sign of the difference as the indicator whether the minuend is less than the subtrahend? So this time we look at -8, which is represented by the bit pattern of 1, 0, 0, 0, and we compare that to 1. Okay? When you look at this, compare it to the case that we just worked with before, you would think that, hey, it should work too because we've got a negative number, positive number. The result is okay. Negative value, positive value should work too. Except this one does not. And now the question is, why is it not working? There are two levels of to that question. The first question is, we'll work out the numbers, the zeros and ones, and see that it is not working. And then the second level of the question is, oh, it's not working because of what reason? Okay, why is it not working? So we'll work out the math. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. I don't even care about the overall borrow because this is all I need. And this time we look at the sign of the difference, and it's a 1. Excuse me, it's a 0. Okay? I look at the 0 and I say it's a 1. I'll make an excellent politician. Because the polygraph will show that, hey, just totally relax. Okay, so a sign of 0 in the difference is telling you that the minuend is not less than the subtrahend. But that is not the case. It really is less than. -8 is less than 1, and yet the sign flag this time is not working. Why is it not working? So the reason why it's not working is when you look at the number wheel, where's -9 on the number wheel for 4-bit numbers? It's not there. The value of the difference is out of range. Because when you look at the value itself, -8 minus 1 is -9. Easy peasy, right? But it cannot be represented as a 4-bit number. So that's why we got a problem here. The sign does not make sense. Which also means it's overflowing. Is that okay? So we'll say this is a case of overflow. All of the other cases have overflow being a 0 because they're not overflowing. Okay, so let's see if we can overflow in the opposite direction, because this time we have a value that is too negative to represent. So can we end up with a case where the value is too positive to represent? Now that one turns out to be easier than you think it is, or most people. We have 0, 0, 0, 0, which is representing the value of 0, minus 1, 0, 0, 0, which is representing the value of negative 8. You would think that, hey, how come this is a problem? But it is. Okay, so I think this subtraction is pretty easy to do. 0 minus 0 is a 0, 0 minus 0 is a 0 with no borrow. 0 minus 0 is a 0, 0 minus 0 is a 0, no borrow. 0 minus 0 is a 0, 0 minus 0 is a 0 with no borrow. 0 minus 1 is a 1 with a borrow, but we don't really care. 1 minus 0 is a 1. We have a sign bit of 1 in the difference, which is telling you that 0 is less than negative 8. That's wrong. Why do we have a problem? If you look at 0 minus negative 8, what is the correct answer in terms of just the value, not the bit representation? 0 minus negative 8 is positive 8. Where is positive 8 on the number wheel for 4 bits? For signed interpretation. It's not there. The most positive value we can represent is 7. 8 is just 1 out of it. So once again, the value that we actually want to represent cannot be represented in 4 bits. So once again, we have an overflow situation. So once again, we have overflow here. So this is why we have an overflow quote-unquote flag to indicate, okay, if you want to remember what the overflow flag is really saying, it's saying the sign flag is lying. Okay? Wait, hold on a second here. The sign flag can only be a 0 or 1. It's binary. It's Boolean, right? The overflow flag is telling you whether the sign flag is lying or not. So if you know what the sign flag is, and you know whether the sign flag is lying, can you deduce the correct answer? Okay. How would you deduce the answer?
Check to see that the overflow flag hasn't been thrown.
Okay.
As if the sign bit.
Okay. So you look at the overflow flag and the sign flag, right? If they are the same, what do you know? Okay, if they're the same, that means the sign flag is saying 0 and it is not lying, or it is saying 1 and it is lying, right? Which means the correct sign is going to be a 0 in both cases. When they agree, okay, when they are the same, that means the correct sign should be a 0. Because it is saying if it's not lying, it is a 0. If it is lying, it is a 1. Which means which means the correct value is a 0. Is that okay? What if the sign flag and the overflow flag disagree? One is a 1, the other one is a 0. What are the two cases? One is the sign flag says it's a 1 and it is not lying. So 1 is indeed the correct sign. Is that okay? The other way around is the sign flag says, nope, the answer is a 0. And the overflow says, no, sign is lying. What is the actual sign in that case? A 1. Oh, okay. So that means if the sign flag and the overflow flag disagree, the actual sign is a 1, which means the minuend is less than the subtrahend. If they agree, that means the actual sign is a 0, which means the minuend is not less than the subtrahend. Is that okay? So this is the reason why we have the overflow flag. Okay, the overflow flag is defined like this. Okay, it's a logical expression. Negation, by the way, only applies to the item immediately to its right-hand side. So when you look at this expression, it means the most significant bit of the minuend x and the negation of the most significant bit of y, which is the subtrahend, and the negation of the most significant bit of the difference. Or, the plus is an or. the negation of the most significant bit of x, which is our n, and the most significant bit of the subtrahend, and the most significant bit of the difference. So this equation will give you the correct overflow. Okay? But overflow by itself is not enough. So now we basically want to look at the combination between the sign and the overflow. So in this case, this sign here is the actual sign, not the sign of the difference, but the actual sign, what it is supposed to be. So if the sign, I take it back. If the sign is a 0 and the overflow is a 0, that means the sign flag is not lying. It really is a 0. If the sign flag is a 0 but the overflow flag is a 1, that means the sign flag says, yeah, it is a 0, but overflow said, nope, sign is lying, which means the actual sign is going to be a 1. Okay, I'm just repeating what I said a little bit earlier, but just relating to the notes. The third line, or the third bullet, it's saying the sign flag says, the actual sign is the sign is a 1 and it is not lying. So the sign really is a 1. And the last one is saying the sign flag says it's a 1, but it's lying, which means the actual sign should be a 0. Yep.
This only works with signed values, what we're saying?
Yes. So this only makes sense when the bit patterns are representing signed values. So is that okay? So when you look at all of these things, we define a new flag that we call the L flag. So the L flag is really the exclusive OR between the sign and the overflow. This is the long way of saying exclusive OR, but basically it is exclusive OR. So the L flag is derived from the sign flag and the overflow flag, and then the overflow flag by itself is derived from the most significant bits of the minuend, subtrahend, and difference. But everything can be done by logic gates. And all logic gates can boil down to transistors. And I have to kind of emphasize that part because we have to make sure that the theoretical stuff that we talk about on paper can actually be done. Because otherwise we'll be talking about a hypothetical computer that does not exist. Yep.
Maybe I'm getting lost in all this. We've answered it before, but how does the computer know if it's signed or not signed again?
The computer does not. Okay, so every time you perform a subtraction, all of these flags will be affected. So every single time you perform a subtraction inside the processor, inside the ALU of the processor, it will affect the overall borrow out. It will affect the sign flag, which is nothing more than the most significant bit of the difference. And it will affect the overflow flag, which is computed using that equation earlier. It looks at the most significant bits of the minuend, subtrahend, and the difference. So all of those things will be computed and stored into what we call a flag register. So the flag register will remember the borrow, sign, overflow, and the L flag. Okay? But its subtraction by itself does not use these flags. It just changes them. Okay? So now the question is, well, what good are we doing just by defining and setting and remembering all of these flags? Yep.
So if you wanted to do a comparison, do you have to specify what flags you're looking at so that you can specify what type of comparison you're doing?
Okay, that's a good question, and the answer is a little bit confusing. There's one instruction to do just comparison. It engages the subtraction mechanism, but it doesn't store the difference. It is computed, but it doesn't store it. Okay? But it does change all the flags. So your L, S, O, and borrow flags, they're all computed and stored somewhere in the processor. Okay? That's the compare instruction. So now you have all of these flags just kind of floating around. Then we have another instruction called a conditional branch instruction that will actually look at these flags to say, okay, are we branching or not depending on the borrow flag? Are we branching or not depending on the L flag? Are we branching or not based on the sign flag? So the only way to make a conditional branch in assembly language is a branch that takes place if and only if a particular flag is set. So the decision-making part is separated from the comparison part. Yep.
So is that why in like x86 there's like a whole family of jump instructions, like J and Z and like J?
Yes.
Okay.
Yep. That is the reason. Yep. The processor that we are using is a RISC processor, so it only gives you the minimal list of conditional branch instructions. Okay. So this is a good time to talk about what is RISC and how it relates to everything that we have talked about up to this point. Okay. So instead of giving you, so right now we have the borrow flag and the L flag, but they're only useful for telling you whether the minuend is less than the subtrahend or not. That's the only thing it can tell you, is whether the minuend is less than the subtrahend. What about less than or equal to? Doesn't do that. Greater than or equal to? Doesn't do that. Greater than? Doesn't do that either. Okay? But we already talked about a little bit earlier. We can do just less than for everything, right?
Yeah.
We also talked about how NAND is enough to emulate NOT, OR, and AND, right? So with a RISC processor, which stands for Reduced Instruction Set Computer, will give you the minimal instructions. Okay, you can make more complicated things out of these minimal instructions, but your program will be longer for sure. Is that okay? Because each instruction cannot do as much. As opposed to a CISC processor, CISC, which stands for Complex Instruction Set Computer, where they give you a gazillion conditional branches. Okay, it will give you less than, greater than, less than or equal to, greater than or equal to, not equal to, and equal to. Okay, so what is the trade-off between CISC and RISC? With CISC, you will need fewer instructions to specify what you need to do, and with RISC, you will need more instructions. So why do we favor RISC?
Less power draw?
Less power draw, but it does less too. So it's not the amount of power that it's using, it is how much energy it uses to perform the fixed amount of processing. Is that okay? So let's think about DVD ripping, okay? So let's say, when you rip The Last Jedi, okay? How much processing is involved, okay? That's a set amount of computation, right? If you do that on a CISC processor, it will take more energy than the same thing done on a RISC processor. That is the bottom line. Okay, are we following this? It's the amount of energy that it takes to perform a certain amount of computation. Now, why is that important? It's not because we are green, we want to save the environment and stuff like that. Why is that important? Well, that too. We don't want to lug around, a big battery on on our phones.
I was going to say, does it just make better use of batteries?
Okay, but yep, go ahead.
Creates more heat.
Creates more heat. Okay, that is the issue. Okay, because how many people have regular LAN parties? Really? Okay. So let's say you have a LAN party and you're inviting, including yourself, there are 4 gamers. Okay. Let's make it 5 because League of Legends needs 5. Okay. So you have 5 gamers, and each one of you has a top of the line super duper gaming computer that has 3 powerful graphics cards. You have the top of the line i9 processor now, right?
Yeah.
How many cores does it have?
I think up to 18.
18 cores. Okay. And you have you have a RAID hard drive, RAID array, instead of just regular hard drive, so that your data doesn't get lost and stuff like that. And you all have big monitors, okay? And then your mom says, well, okay, you guys can only do this in your own room. And let's say you have a fairly big room, maybe 12 by 12, that's kind of good size. You can accommodate 5 game workstations. Okay, so we have 2 big problems now. Each computer setup is a 1 kilowatt setup. and you have 5 of those, right? So that means you're dealing with a 5 kilowatt power consumption issue. So the first thing that's going to happen is it's going to pop the circuit breaker.
Yeah.
Okay? So you tell your parents, go like, can we hire an electrician to rewire everything so that we have 3 breakers going to my room? The parents go like, okay, if you're paying for it, and you're thinking, I can take my student loan and apply it over here. So now you have your room rewired, okay? You have 3 circuit breakers going to one single room to make sure that there's enough power. So now your friends are all happy, starting with the computer, and it's on the coldest day of the winter. And you guys are just going like, oh, this is kind of nice, it's kind of warm, okay? And then half an hour later, what's going to happen? It's going to get hot, right? You open all the windows. And is that going to be enough? 5 kilowatts is equivalent to how many electric heaters? We're talking about the type you buy from Target, okay? Those are 1800 watt heaters, right? So let's call it maybe a third of 5 kilowatts. So you're basically running 3 electric heaters at full power all the time when you're gaming. It doesn't take much time to heat up a room that is 12 by 12 to the point where you cannot stand it. Okay? Okay, but that's just a gaming situation. Okay, you're not even trying to pack as much processing power as you want into a space that is as small as possible. Who really wants to do that? Google, Facebook, all of these services in the cloud. Well, we think of these things as in the cloud, right? There's no physical form, but something has to do all the computation, right? So the data center of Google, the data center for Facebook, and all of that stuff, they have this big issue because they want to use as much they want to have as much processing power as possible. But the limiting factor is not how much power they can pump into the building. That's easy. You can build a data center around a nuclear plant. It's not a problem. The problem is how do you extract all the heat out of the building. That becomes a big issue. So that is why all of these data centers are using RISC processors. They're using the same kind of processor that you have on the cell phone because they are the most energy efficient processors. They use the least amount of energy to perform the same amount of calculation. So that is why we have this big shift from CISC to RISC. It is for your cell phone, so you don't have to carry like this big of a battery around. It is for the data center as well. Okay, I know we are running out of time, but there's one more question, okay? Because skepticism is a good thing. So why do we still have CISC processors in these guys? When RISC is so great, okay? Why are we still using CISC? Because the i8, i7, i9 processors, they're CISC processors. Why don't we switch to CISC processors everywhere? Obviously, we can pack a lot of processing power. Even though one RISC processor doesn't do a whole lot, we just have more of those. They're more energy efficient. So in the end, you can get the same amount of work done and just as fast as a CISC processor. But why are we still using CISC processors? Space? No, not so much of a space issue.
Development time?
Development time. You're getting closer. We're getting warmer. No pun intended. Okay, think about Linux. Are there variants of Linux that run on RISC processors? Tons. Okay, every time there's a RISC processor coming up, Linux can run on it. What about Windows? Not so much, right? They're starting, but they have tried many times.
Yeah.
Okay, so the limiting factor is not, is because of the operating system. The whole tool chain, your compiler, your operating system, and all the applications. When someone comes up with a new processor, like a new really energy efficient RISC processor that has no backward compatibility with other processors, what happens to the people using Linux? They port Linux, right? And when they port Linux, they're porting the compiler, they're porting the operating system itself. But once the compiler is ported and the core part, the kernel is ported, everything is just recompiled. Okay? Why do you think that is an issue with Windows?
There's less people that would contribute to that.
Well, that's not the key issue. The key issue is their tool chain. I'm suspecting their tool chain is not very easy to retarget a new architecture. They cannot change the compiler to retarget a new architecture quickly. They cannot retarget the kernel itself to a new architecture easily. Whereas Linux is fairly easy because most of the code is written in plain C. So once you have the small percentage of assembly code ported, the rest is just recompiling. But with Windows, I'm suspecting they have a lot of architecture-dependent code that makes it kind of difficult to port to a new architecture. So we'll continue this discussion next time because I can show you how many platforms are supported by Linux as opposed to how many platforms are supported by Windows. And you will start to realize, oh, okay, why is that? All right, I'll see you guys over at the lab.